Rogue planets represent one of the most enigmatic and captivating mysteries of space. These celestial bodies are planets that do not orbit a star and instead drift through the galaxy in isolation, untethered to any solar system. Unlike planets in our solar system that revolve around the sun, rogue planets move through interstellar space without a parent star. This distinct feature of rogue planets raises profound questions about their origin, behavior, and impact on the broader cosmic environment. By delving deep into the nature of rogue planets, we can explore their mysterious formation processes, their potential for harboring life, and how they challenge our understanding of planetary science. The discovery of rogue planets only came in recent decades, aided by advances in astronomical technology. These planets are difficult to detect because they do not emit light like stars, and since they are not part of a solar system, they do not reflect much light from a host star either. Despite these challenges, astronomers have developed indirect methods of detecting rogue planets, most notably through gravitational microlensing. This technique relies on the gravitational field of rogue planets bending and magnifying the light from distant stars as they pass between Earth and the distant light source. The bending of light reveals the presence of an otherwise invisible rogue planet. One of the first questions raised by the existence of rogue planets is how they form. There are two primary theories regarding their origins. One possibility is that rogue planets are born in a similar fashion to other planets, forming within the swirling disk of dust and gas surrounding a young star. However, during the chaotic early stages of a solar system's development, gravitational interactions between planets and other large objects can be violent and unpredictable. Some planets may be flung out of their orbits, ejected from the gravitational grasp of their parent star, and sent hurtling into the void of interstellar space. This process, known as planetary ejection, is believed to be a common occurrence in the early lives of solar systems, and many rogue planets could be the result of these violent dynamics. Another theory suggests that rogue planets may form independently of stars altogether. Just as stars formed from the collapse of massive clouds of gas and dust, it's possible that smaller clumps of material could collapse to form planets without the necessary mass to ignite nuclear fusion and become stars. These free-floating planets would never have orbited a star in the first place, forming directly as independent objects in interstellar space. This theory expands the potential variety of rogue planets, suggesting that some may have originated in isolation rather than being cast out from a solar system. One of the most intriguing aspects of rogue planets is the possibility that some of them could harbor life, even without the warmth and light of a nearby star. At first glance, it might seem that a planet drifting through the cold, dark expanse of space would be an inhospitable place for life. Without a star, a rogue planet would lack a consistent source of energy, and its surface could be frozen solid. However, the potential for life on rogue planets cannot be dismissed so easily. There are several mechanisms by which a rogue planet might retain the necessary conditions for life, even in the absence of a star. One possibility is that rogue planets could have thick atmospheres composed of gases like hydrogen that trap heat. This greenhouse effect could prevent the planet from cooling to the point where liquid water, a key ingredient for life, freezes entirely. The internal heat generated by radioactive decay within the planet's core could also play a crucial role in maintaining subsurface oceans or other reservoirs of liquid water. On Earth, life thrives in some of the most extreme environments, from deep-sea hydrothermal vents to underground caves. If similar conditions exist on rogue planets, life could potentially survive beneath the surface, where heat from the planet's interior provides the necessary energy. In addition to internal heating, rogue planets might also benefit from tidal forces generated by interactions with moons or other celestial bodies. These tidal forces could create friction within the planet's interior, generating additional heat and maintaining the potential for liquid water. The discovery of subsurface oceans on moons like Europa and Enceladus in our own solar system suggests that liquid water can exist beneath icy surfaces, even far from the sun. A similar phenomenon could occur on rogue planets, raising the tantalizing possibility that life could exist in hidden, underground environments on these wandering worlds. The potential for life on rogue planets also raises questions about how we might detect it. Since these planets are not illuminated by a nearby star, traditional methods of searching for habitable planets, such as detecting atmospheric signatures of water or oxygen in starlight, are not feasible. Instead, scientists must rely on indirect methods, such as studying the planet's heat emissions or searching for signs of geothermal activity. In the future, more advanced technologies, such as space telescopes equipped with powerful infrared sensors, may allow us to detect the faint heat signatures of rogue planets and study their atmospheres in more detail. Rogue planets also challenge our understanding of the architecture of the galaxy. For much of human history, the prevailing view was that planets existed only within solar systems, orbiting stars like the Sun. However, the discovery of rogue planets suggests that planets may be far more common and varied than previously thought. Estimates suggest that there could be as many rogue planets in the Milky Way as there are stars, if not more. This abundance of rogue planets implies that planetary formation is a more diverse and dynamic process than once believed, capable of producing not only planets in stable orbits around stars, but also planets that roam the galaxy freely. The sheer number of rogue planets raises interesting possibilities about the future of space exploration. As humanity continues to venture further into space, rogue planets could become important waypoints or destinations. If some of these planets possess subsurface oceans or other resources, they could serve as critical outposts for future spacefaring civilizations. Additionally, the study of rogue planets could provide valuable insights into the formation and evolution of planets in general. By understanding how rogue planets form, migrate, and survive in the harsh conditions of interstellar space, we gain a deeper understanding of the forces that shape planetary systems and the galaxy as a whole. The presence of rogue planets also adds complexity to the search for extraterrestrial life. If planets are not confined to solar systems, the potential habitats for life in the galaxy expand dramatically. Life could potentially exist on rogue planets drifting through the galaxy, entirely independent of any star. This realization forces us to rethink the parameters of the search for life, as rogue planets could represent hidden refuges for life beyond the conventional boundaries of habitable zones around stars. Moreover, rogue planets raise profound philosophical questions about the nature of isolation and survival. These planets exist in the vast, empty spaces between stars, far from the life-sustaining warmth of a sun. Yet, despite their isolation, rogue planets may still possess the conditions necessary for life. They represent a form of cosmic solitude, wandering through space without a star to call home, yet potentially harboring the building blocks of life deep within their frozen surfaces. As we continue to study rogue planets, we are likely to uncover new and surprising facts about these elusive worlds. Each discovery brings us closer to understanding the full diversity of planetary systems in the universe, as well as the potential for life in unexpected places. Rogue planets serve as a reminder that the universe is full of mysteries waiting to be unraveled, and that life, in its many forms, may exist in the most unlikely of environments. The future of rogue planet research holds promise, with new technologies and missions set to explore these fascinating objects. Missions like the Nancy Grace Roman Space Telescope, which is set to launch in the coming years, will provide new opportunities to detect and study rogue planets. These advancements will allow astronomers to identify more rogue planets, study their atmospheres, and investigate the possibility of life on these wandering worlds. As we push the boundaries of our knowledge, rogue planets will continue to inspire curiosity and challenge our assumptions about the nature of planets, life, and the universe itself. Rogue planets offer a window into some of the most fundamental processes in planetary and cosmic evolution. Their very existence challenges long-held assumptions about what a planet is and how planets form, compelling astronomers to reconsider the dynamics of star systems. Traditional planetary formation models suggest that planets are born within protoplanetary disks surrounding young stars, slowly accumulating mass through the collision and coalescence of dust, rock, and gas. As the planets grow, they stabilize into orbits around their parent stars, and their fate is largely shaped by the gravitational pull of the star. However, rogue planets exist outside of this framework, which suggests that their origin stories could either be deeply chaotic or completely independent of star systems. To understand more about rogue planets, it is important to delve deeper into their ejection mechanisms. In a nascent planetary system, the gravitational interplay between planets, stars, and other celestial objects can be incredibly turbulent. Planets might form in relative peace, but as they grow and begin to interact with each other, their orbits can become unstable. If one planet gains more mass or moves closer to another planet, their combined gravitational forces may alter their paths, potentially leading to catastrophic interactions. Some planets may collide, while others might be flung out into space altogether. This is where rogue planets likely come into the picture. The concept of planetary ejection has been modeled extensively in computer simulations, which show that these interactions are more common than one might expect. As larger planets interact with their host star and their fellow planets, smaller planets, particularly those on the outskirts of the system, may be the most vulnerable to ejection. As these smaller bodies are sent out into the void, they become rogue planets, forever severed from the warmth of their parent star. The ejection process is violent, but it helps to explain the sheer number of rogue planets that might exist. It's estimated that for every star in the galaxy, there could be at least one rogue planet, meaning that rogue planets might outnumber stars by a wide margin. This startling realization leads to profound implications for our understanding of planetary systems and galactic structure. If rogue planets are so numerous, they may play a much larger role in the galaxy's ecology than previously thought. They might even influence star formation and galactic evolution, as their gravitational fields could interact with other stars, nebulae, and celestial bodies during their long journeys through space. Moreover, the existence of rogue planets suggests that planetary formation is not as tightly bound to stars as previously thought. Some rogue planets could have formed through direct collapse, a process where a planet-sized body forms from the gravitational collapse of a molecular cloud rather than the disk of material surrounding a star. This type of formation challenges the idea that planets need stars to form, suggesting that planetary bodies might arise in a variety of environments, including in isolation. This notion vastly expands the types of planets that could exist and where they might be found. One of the most perplexing aspects of rogue planets is their long-term survival. How do these planets, isolated from the life-giving energy of a star, sustain themselves in the cold, dark expanse of space? The answer lies in their ability to retain heat from various sources. Some rogue planets may be able to retain heat from their formation, slowly radiating away the energy accumulated during their violent birth. This residual heat might allow them to maintain liquid water beneath icy surfaces, similar to moons like Europa and Enceladus, which host subsurface oceans heated by gravitational interactions with their parent planets. Additionally, rogue planets may also possess radioactive elements within their cores, which could produce heat through radioactive decay. This internal heating could keep parts of the planet warm enough for life to thrive, even in the absence of a star. On Earth, extremophiles, organisms that live in extreme environments, thrive in conditions that are far removed from the surface, such as deep-sea hydrothermal vents. These organisms derive energy from the heat and chemicals released by the Earth's interior, rather than sunlight. If similar conditions exist on rogue planets, life could potentially emerge in these isolated environments, hidden beneath kilometers of ice or rock. One of the major challenges facing scientists is detecting these rogue planets. Without the light of a parent star, rogue planets are incredibly difficult to observe directly. Traditional methods of planetary detection, such as the transit method, which looks for dips in a star's brightness as a planet passes in front of it, or the radial velocity method, which detects the gravitational wobble a planet exerts on its star, are useless in the case of rogue planets. Instead, astronomers have turned to gravitational microlensing, a technique that relies on the warping of spacetime caused by a massive object, such as a rogue planet. Gravitational microlensing occurs when a rogue planet passes in front of a distant star. As the planet's gravity bends and magnifies the light from the star, astronomers on Earth can detect the brief flare in brightness. While this method is effective, it is also rare and difficult to observe. Gravitational microlensing events are short-lived and unpredictable, requiring constant monitoring of vast regions of space. Despite these challenges, microlensing has proven to be one of the most promising methods for discovering rogue planets. In 2016, a groundbreaking study using microlensing data from the Optical Gravitational Lensing Experiment, OGLE, suggested that there could be billions of rogue planets in the Milky Way alone. These findings opened up new avenues of exploration as astronomers began to realize just how common rogue planets might be. Each new discovery pushes the boundaries of our understanding of planetary science and raises new questions about the potential for life beyond our solar system. The search for rogue planets is set to receive a significant boost with the launch of the Nancy Grace Roman Space Telescope. This next-generation space telescope will be equipped with the tools necessary to detect more rogue planets through microlensing, and its advanced infrared capabilities will allow astronomers to study these objects in greater detail than ever before. By observing rogue planets across a wide range of wavelengths, scientists hope to learn more about their atmospheres, compositions, and potential for harboring life. Beyond their scientific value, rogue planets have captured the imagination of the public and science fiction writers alike. These solitary wanderers evoke feelings of cosmic loneliness and isolation, drifting through the void without the companionship of a star. In science fiction, rogue planets often serve as mysterious and foreboding locations, where explorers face the unknown and encounter the unexpected. The concept of a planet roaming freely through space has inspired countless stories about the fragility of life and the vast, uncaring nature of the cosmos. However, rogue planets are not just a product of imagination, they are real, tangible objects that challenge our understanding of the universe. Their existence raises profound philosophical questions about the nature of planets, life, and the cosmos. How do we define a planet if it does not orbit a star? What does it mean for life to exist in complete isolation from the light of a sun? And how do rogue planets fit into the broader narrative of the universe's evolution? These questions are not just academic, they have real implications for the future of planetary science and space exploration. As we continue to study rogue planets, we may discover new forms of life, new types of planetary systems, and new ways of thinking about our place in the universe. Rogue planets challenge the very foundations of planetary science, forcing us to reconsider the processes that shape worlds and the potential for life in the most unexpected places. As rogue planets challenge our traditional conceptions of planetary formation and cosmic evolution, they also open up new possibilities for the search for extraterrestrial life. The notion that a planet can exist independently from a star yet still potentially harbor life is a paradigm shift in astrobiology. Until recently, much of the search for life beyond Earth has been focused on the so-called habitable zone around stars, the narrow region where conditions are just right for liquid water to exist on the surface of a planet. However, rogue planets suggest that life might be able to survive in environments far removed from this habitable zone, relying on entirely different sources of energy. This idea is not as far-fetched as it might initially seem. Earth's deep-sea ecosystems, thriving around hydrothermal vents on the ocean floor, are a prime example of life existing without direct sunlight. These ecosystems are powered by chemosynthesis, a process by which organisms convert chemicals released by the Earth's interior into energy. If rogue planets possess similar geothermal activity, perhaps driven by tidal forces, residual heat from formation, or radioactive decay, they might be able to support similar ecosystems beneath their surfaces. The search for life, therefore, could extend beyond planets in traditional orbits to include rogue planets floating through the darkness of interstellar space. In fact, some scientists argue that rogue planets could be more favorable for the development of life than previously thought. Unlike planets orbiting stars, rogue planets are not subject to the violent flares, radiation, and variability of their host star, which could create more stable conditions for life. This stability, combined with the potential for internal heat sources, might make rogue planets surprisingly hospitable in certain cases. Additionally, rogue planets could drift through interstellar clouds of gas and dust, picking up materials that could contribute to complex chemistry and the emergence of life. One of the most exciting aspects of rogue planets is their ability to travel vast distances through space. A rogue planet that forms in one region of the galaxy could potentially travel for millions or even billions of years, passing through different environments, interacting with other celestial objects, and even entering the gravitational influence of other star systems. This means that rogue planets could serve as vehicles for the transport of life or organic materials across the galaxy, potentially seeding other planetary systems with the building blocks of life. This idea, known as panspermia, suggests that life on Earth, or elsewhere in the universe, could have been brought here by rogue planets or other cosmic travelers. While the idea of rogue planets as life-bearing objects is speculative, it is a fascinating possibility that underscores the need for more exploration and study. The discovery of a rogue planet with signs of habitability would be one of the most significant breakthroughs in astrobiology, as it would demonstrate that life can exist in environments far beyond the traditional habitable zone. Such a discovery would also raise new questions about the prevalence of life in the universe and the ways in which life can survive and evolve in extreme conditions. The study of rogue planets also has implications for our understanding of planetary migration and the history of our own solar system. It is possible that rogue planets played a role in shaping the orbits of planets in the early solar system, or that some of the outer planets in our system were once rogue planets that were captured by the sun's gravity. In fact, there are theories suggesting that some of the distant objects in the outer reaches of our solar system, such as those in the Oort cloud or Kuiper belt, could have originated as rogue planets or planetary fragments that were captured by the sun's gravity long ago. This raises the possibility that rogue planets could occasionally be captured by other star systems as well. If a rogue planet passes close enough to a star, its gravity could pull the planet into orbit, effectively adopting it as a new member of the planetary system. This process, known as gravitational capture, could explain the presence of some planets with highly eccentric or unusual orbits. It also suggests that planetary systems are not as closed or static as once thought. Planets can come and go, and a system's composition can change over time as rogue planets pass through and interact with the system's gravity. Another intriguing aspect of rogue planets is the possibility that they could collide with other celestial objects, such as stars or planets, during their long journeys through space. These collisions could have catastrophic consequences, potentially reshaping entire planetary systems or even triggering the formation of new stars or planets. Rogue planets could also interact with star-forming regions, adding mass to protostellar clouds and influencing the process of star and planet formation in ways that are not yet fully understood. In the case of a rogue planet entering our solar system, the consequences could be dramatic. Depending on the size and trajectory of the rogue planet, its gravitational influence could perturb the orbits of planets, moons, and other objects in the solar system. In extreme cases, a close encounter with a large rogue planet could even eject planets from their orbits or send them spiraling into the sun. While the likelihood of such an event occurring is relatively low, the potential consequences highlight the dynamic and sometimes chaotic nature of planetary systems. The study of rogue planets also intersects with the search for dark matter, the mysterious substance that makes up most of the mass in the universe. While dark matter remains elusive, some scientists have speculated that rogue planets could help shed light on its nature. Since rogue planets do not emit light and are difficult to detect, they share some similarities with the way dark matter behaves. Some have proposed that there could be a connection between rogue planets and dark matter, or that the study of rogue planets could provide new insights into the distribution and properties of dark matter in the galaxy. Despite the challenges involved in detecting and studying rogue planets, advancements in technology are bringing us closer to unlocking their mysteries. Future space telescopes, such as the James Webb Space Telescope and the aforementioned Nancy Grace Roman Space Telescope, are expected to revolutionize our ability to detect rogue planets, particularly those that might be warm enough to emit detectable infrared radiation. These telescopes will also allow astronomers to study the atmospheres and compositions of rogue planets in unprecedented detail, providing valuable clues about their origins and potential for habitability. In addition to space-based telescopes, ground-based observatories equipped with advanced adaptive optics systems and large-diameter mirrors will play a key role in the study of rogue planets. These observatories will be able to detect the subtle gravitational effects of rogue planets on distant stars and search for the faint glimmers of light that might indicate the presence of a rogue planet's atmosphere or surface features. The discovery of rogue planets has profound implications for our understanding of the universe and our place within it. These solitary wanderers challenge our assumptions about planetary formation, migration, and habitability, and they remind us that the cosmos is far more complex and dynamic than we once imagined. As we continue to explore the vast expanse of space, rogue planets will undoubtedly play a central role in shaping our understanding of the galaxy and the potential for life beyond Earth. As the study of rogue planets progresses, it also forces us to reconsider the nature of planetary classification and what it truly means to be a planet. The traditional definition of a planet is one that orbits a star, but rogue planets challenge this definition by existing entirely outside the gravitational influence of any star. This has led some astronomers to suggest that rogue planets might belong to a distinct category of celestial objects altogether, perhaps more akin to failed stars or large asteroids. The lines between these classifications are becoming increasingly blurred as we learn more about the diversity of objects in the universe. The size of rogue planets can vary dramatically, from massive objects several times the size of Jupiter to smaller, Earth-sized planets or even planet-like objects on the boundary between planets and asteroids. This wide range of sizes adds to the difficulty in defining exactly what a rogue planet is and how it should be categorized. The larger rogue planets, sometimes referred to as brown dwarfs, may have formed in a similar manner to stars but failed to ignite nuclear fusion due to insufficient mass. These massive rogue planets could also host moons, creating mini planetary systems of their own as they drift through space. The moons of rogue planets represent another intriguing avenue for exploration. Just as moons around planets in traditional orbits can possess subsurface oceans or atmospheres, the moons of rogue planets might also be capable of supporting life, particularly if they have internal heat sources like tidal heating. In fact, some scientists argue that the moons of rogue planets might be more likely to host life than the rogue planets themselves, as the gravitational interactions between the planet and its moons could generate significant amounts of heat, providing the necessary energy for life to thrive even in the cold depths of interstellar space. The potential for life on rogue planets and their moons also raises philosophical and existential questions about our understanding of life in the universe. If life can exist on rogue planets, far from the warmth of a star, then it suggests that life is far more adaptable and resilient than we ever imagined. This has profound implications for the search for extraterrestrial life, as it widens the scope of potential habitats where life might be found. Rather than being limited to planets in the habitable zones of stars, life might be able to emerge and persist in environments that we previously considered too extreme or inhospitable. Moreover, the discovery of life on a rogue planet would challenge our understanding of the conditions necessary for life to evolve. It would suggest that life does not necessarily need sunlight or even a stable climate to survive, but could instead rely on other energy sources, such as geothermal heat or chemical reactions. This would expand the range of potential habitats for life across the galaxy and raise new questions about the diversity of life forms that might exist in the universe. In addition to their potential role in the search for life, rogue planets also offer insights into the processes of planetary formation and destruction. Some scientists believe that rogue planets are the remnants of failed planetary systems, ejected from their original orbits by gravitational interactions with other planets or stars. This process of planetary ejection, known as dynamical instability, is thought to have occurred frequently in the early stages of planetary system formation, as newly formed planets jockeyed for position and occasionally collided or flung each other into space. These ejected planets, now rogue planets, provide valuable clues about the chaotic nature of planetary formation and the delicate balance that must be maintained for a planetary system to remain stable. By studying rogue planets, astronomers can learn more about the processes that shape planetary systems and the factors that lead to their stability or collapse. This, in turn, can inform our understanding of the history of our own solar system and the events that shaped its formation. The idea that rogue planets are ejected members of planetary systems also raises the possibility that our solar system could have once had more planets than it does today. If planets were ejected from the early solar system, they could now be wandering through space as rogue planets, forever disconnected from the Sun. This idea has led some scientists to speculate about the existence of Planet 9, a hypothetical rogue planet that might once have been part of the solar system but was flung into a distant, elliptical orbit or ejected altogether. While the existence of Planet 9 remains speculative, the search for such objects highlights the importance of rogue planets in understanding the architecture and evolution of planetary systems. The detection of a rogue planet that was once part of our solar system would be a groundbreaking discovery, shedding light on the early history of our planetary system and the forces that shaped its current configuration. The detection of rogue planets also presents significant challenges due to their lack of a central star. Traditional methods of detecting planets, such as observing the wobble of a star caused by a planet's gravitational pull or the dimming of a star's light as a planet passes in front of it, are not applicable to rogue planets. Instead, astronomers must rely on indirect methods, such as gravitational microlensing, which occurs when a rogue planet passes in front of a distant star, temporarily magnifying its light due to the planet's gravitational field. Gravitational microlensing has already led to the discovery of several rogue planets, but it is a rare and fleeting event, making it difficult to study these planets in detail. Other detection methods, such as infrared observations, can be used to search for rogue planets that emit heat, but these methods are limited by the sensitivity of current instruments and the vast distances involved. Despite these challenges, ongoing advancements in technology are making it increasingly possible to detect and study rogue planets. The development of more powerful telescopes, both on the ground and in space, will allow astronomers to search for rogue planets in greater detail and over larger areas of the sky. In particular, the use of large-scale sky surveys and sophisticated data analysis techniques will enable the detection of even fainter and more distant rogue planets than ever before. As our ability to detect and study rogue planets improves, so too will our understanding of their role in the broader context of the universe. Rogue planets are not isolated objects, but are part of the dynamic and interconnected web of celestial bodies that make up the cosmos. Their movements through space, their interactions with other planets and stars, and their potential to host life all contribute to the richness and complexity of the universe. The existence of rogue planets also underscores the vastness and unpredictability of space. These planets, drifting alone through the darkness, serve as a reminder that the universe is full of surprises and that our understanding of it is still in its infancy. The study of rogue planets is just one piece of the larger puzzle of cosmic exploration, but it is a piece that has the potential to reshape our understanding of planetary science, astrobiology, and the nature of the universe itself. In the coming decades, as new technologies and missions are developed, we can expect to learn much more about rogue planets and their role in the galaxy. Whether they are solitary wanderers, remnants of failed planetary systems, or potential harbors for life, rogue planets will continue to captivate the imagination of scientists and the public alike. They represent the ultimate mystery, planets without stars, drifting through the void, their secrets waiting to be uncovered by the next generation of explorers. The discovery of rogue planets also raises profound questions about the fate of planets in general. Over the course of a star's lifetime, significant changes occur in its environment, particularly as stars age and evolve into red giants or supernovae. When a star reaches the end of its life, the gravitational balance that once held a planetary system together can become unstable. This instability could result in the ejection of planets, turning them into rogue planets as they are flung out of their original orbits and sent into the cold expanse of interstellar space. This process suggests that some rogue planets might be older than we imagine, having once orbited stars that have long since died, making these planets relics of ancient systems. The idea that rogue planets may represent the final stage in the life cycle of planets raises important implications about the future of our own solar system. When the Sun eventually enters its red giant phase, expanding to engulf the inner planets, the outer planets, such as Jupiter, Saturn, Uranus, and Neptune, may also face destabilization. Gravitational interactions between the dying Sun and the remaining planets could lead to ejections, turning some of them into rogue planets that drift away from the solar system forever. In this scenario, even planets as large as Jupiter or Saturn might one day find themselves alone in the dark, free from the gravitational pull of any star. This distant future of planetary ejection is not limited to our solar system. Throughout the galaxy, as stars age and die, planets that once orbited them could be cast off into space, creating a steady stream of newly minted rogue planets. Some estimates suggest that the number of rogue planets could outnumber the stars in the Milky Way, with hundreds of billions of these lonely wanderers drifting between the stars. This staggering number emphasizes just how common and significant rogue planets might be in the broader structure of the galaxy, playing a critical but largely unseen role in its overall dynamics. One of the most fascinating aspects of rogue planets is the idea that they could serve as natural laboratories for understanding the limits of planetary habitability. Without the steady energy from a star, how could any form of life possibly survive on a rogue planet? While the surface conditions on most rogue planets would likely be frozen and inhospitable, there are several theories that suggest life could still thrive in certain environments beneath the surface. For example, a thick atmosphere rich in greenhouse gases could trap enough heat to keep a rogue planet's surface warm for a considerable amount of time after it has been ejected from its star system. If the rogue planet has a molten core, geothermal heat could provide a long-lasting energy source for subsurface oceans or lakes, potentially creating environments where microbial life could survive. These warm oases beneath the surface of rogue planets might remain stable for millions, if not billions, of years, offering a refuge for life even in the harshest conditions of deep space. The presence of subsurface oceans on rogue planets would be similar to moons in our solar system, such as Europa or Enceladus, where liquid water exists beneath a thick icy crust. On these moons, tidal forces from their parent planets generate enough heat to keep the water in a liquid state, even in the cold outer regions of the solar system. A rogue planet with similar internal heat sources might have the same capacity to maintain liquid water beneath its surface, providing a potential habitat for life despite the absence of sunlight. This idea is particularly compelling when considering the discovery of extremophiles, organisms that can survive in extreme conditions, on Earth. Extremophiles have been found in environments as varied as the deep ocean, geothermal vents, and even in the icy permafrost of Antarctica, where temperatures can plunge well below freezing. These organisms demonstrate that life is remarkably adaptable and can thrive in conditions once thought to be inhospitable. If life on Earth can survive in such extreme environments, it raises the possibility that similar life forms could exist on rogue planets, adapting to the unique challenges of life without a star. Rogue planets might also experience occasional heating events as they pass close to other stars or even interact with other planetary systems. Such flybys, while rare, could temporarily heat a rogue planet's surface, melting ice and creating liquid water. These events might be short-lived, but they could provide brief windows of habitability where life could emerge or reactivate from a dormant state. Additionally, rogue planets might encounter interstellar clouds or regions of gas and dust as they travel through the galaxy. These clouds could provide temporary sources of heat and materials that could be absorbed by the rogue planet, potentially altering its atmosphere or surface conditions. While these encounters would be relatively infrequent, they add another layer of complexity to the rogue planet's journey through space, offering yet another possible mechanism for sustaining life or altering the planet's environment. Interestingly, rogue planets also present a unique opportunity for exploration. While they are harder to detect and observe than planets orbiting stars, the discovery of a rogue planet passing relatively close to Earth could open the door to an unprecedented exploration mission. With no central star to contend with, a probe could approach a rogue planet more easily, studying its atmosphere, surface, and any potential moons in detail. Such a mission could provide invaluable insights into the nature of rogue planets and help answer some of the most pressing questions about their formation, composition, and potential for life. The study of rogue planets is also connected to broader questions about the formation and evolution of planetary systems. If rogue planets are the remnants of failed planetary systems or the victims of gravitational ejection, they provide a window into the early, chaotic stages of planet formation. By studying these planets, astronomers can gain a better understanding of the forces that shape planetary systems and the conditions that lead to their stability or collapse. This knowledge could have important implications for our understanding of exoplanets, planets orbiting other stars, as well as for the future of our own solar system. The potential for rogue planets to host life also adds a new dimension to the search for extraterrestrial intelligence, SETI. Traditionally, the search for extraterrestrial life has focused on planets orbiting within the habitable zones of stars, where conditions are thought to be most favorable for life. However, the discovery that rogue planets could also support life suggests that we may need to expand our search to include these wandering worlds. While the chances of detecting life on a rogue planet are remote, the possibility cannot be ruled out, and it offers yet another avenue for exploration in the quest to answer the age-old question: are we alone in the universe? Rogue planets represent a fascinating and largely unexplored frontier in planetary science. Their existence challenges our traditional notions of what it means to be a planet, raises profound questions about the nature of planetary habitability, and offers new insights into the processes that shape planetary systems. As our technology improves and our understanding of the universe deepens, the study of rogue planets is sure to yield even more surprises and discoveries, further expanding our knowledge of the cosmos and our place within it. While much remains unknown about rogue planets, their study is already beginning to reshape our understanding of the universe. From their mysterious origins to their potential to harbor life, rogue planets are among the most intriguing and enigmatic objects in space. As scientists continue to explore these lonely wanderers, they may hold the key to unlocking some of the greatest mysteries of the cosmos, revealing new insights into the formation, evolution, and diversity of planetary systems throughout the galaxy. Rogue planets also push the boundaries of our understanding of how planetary atmospheres can evolve in isolation. Planets that are free-floating, far from the influence of a parent star, could still retain or even develop unique atmospheres. The atmosphere of a rogue planet might be primarily influenced by internal geological processes, including volcanic activity, outgassing, and the interactions of various gases within the planet's core and mantle. This would create an atmosphere completely different from planets orbiting stars, where stellar winds and radiation significantly shape atmospheric composition. These planets may have thick, dense atmospheres that trap heat efficiently, possibly preventing the surface from freezing solid despite the planet's isolation in the cold depths of space. Such an atmosphere could contain high concentrations of greenhouse gases like carbon dioxide or methane, which could theoretically maintain a livable temperature for extended periods. It is even conceivable that some rogue planets might generate enough heat internally through radioactive decay, tidal forces, if they once had moons, or residual heat from their formation to sustain liquid water under their surfaces. One of the most exciting questions about rogue planets is whether they could possess subsurface oceans, like the icy moons of Jupiter and Saturn in our solar system. On moons like Europa and Enceladus, thick layers of ice cover global oceans of liquid water that are warmed by tidal forces. If a rogue planet has similar internal heat sources, it could potentially host life in such oceans, shielded from the harsh, frozen surface conditions. Even without tidal heating, radioactive decay or residual heat from planetary formation might keep subsurface oceans warm for billions of years, creating a stable, long-term environment for microbial life to evolve and survive. Interestingly, rogue planets might also serve as cosmic time capsules, preserving clues about the environments of their original star systems. Since these planets have been ejected from their stellar nurseries, their atmospheres and geologies could retain signatures from the primordial conditions in which they formed. This could include traces of the chemical composition of the original star system, the planet's interactions with other celestial bodies during its early years, and any processes that led to its eventual ejection. By studying rogue planets, scientists might be able to reconstruct the history of planetary systems and better understand the processes that lead to planetary formation and evolution. One of the major challenges in studying rogue planets is that they are incredibly difficult to detect. Without the light of a star to illuminate them, rogue planets are nearly invisible to most observational techniques that astronomers use to study exoplanets. However, advances in technology and new detection methods are beginning to shed light on these elusive worlds. One promising technique is gravitational microlensing, which occurs when a rogue planet passes in front of a distant star. The planet's gravity acts like a lens, magnifying the light from the star and temporarily increasing its brightness. By carefully analyzing these events, astronomers can infer the presence of a rogue planet, even though it remains invisible. Another technique involves detecting the faint infrared glow of a rogue planet's heat. Even in the cold of interstellar space, rogue planets still emit some heat, especially if they have internal energy sources or if they are still radiating heat from their formation. This faint thermal radiation can be picked up by infrared telescopes, which can then be used to estimate the planet's size, composition, and even some aspects of its atmosphere. As infrared technology improves, we may be able to detect more rogue planets and learn more about their characteristics. The discovery of rogue planets challenges us to rethink our models of planet formation and planetary dynamics. For many years, the dominant model of planet formation, known as the core accretion model, focused on planets forming within the protoplanetary disks around young stars. According to this model, planets form as small particles of dust and ice collide and stick together, gradually growing larger over time. However, this model does not fully explain how planets can be ejected from their star systems or how planets might form in isolation without the influence of a nearby star. The discovery of rogue planets suggests that alternative or additional mechanisms might be at play, and that planet formation might be more complex and varied than previously thought. One alternative theory is that rogue planets might form in the same way that stars do, through the collapse of large clouds of gas and dust. In this model, known as the gravitational collapse model, rogue planets form in isolation, directly from the collapse of a gas cloud, without ever being part of a stellar system. This would mean that rogue planets are more like failed stars than traditional planets, forming from the same process that gives birth to stars but not accumulating enough mass to ignite nuclear fusion and become a star themselves. These failed stars, known as sub-brown dwarfs or planetary mass objects, could then drift through space as rogue planets. This raises another interesting possibility, that rogue planets might exist in a continuum with other celestial objects, such as brown dwarfs and low-mass stars. Brown dwarfs are objects that are too large to be considered planets but too small to sustain the nuclear fusion reactions that power stars. Some brown dwarfs have been discovered floating freely in space, without orbiting any star. These objects share many characteristics with rogue planets, suggesting that there might not be a clear distinction between rogue planets and other free-floating objects. Instead, there might be a spectrum of planetary mass and stellar mass objects, all existing independently of any star system. The discovery of rogue planets also has implications for our understanding of planetary systems as a whole. If rogue planets are common, it suggests that planetary systems are not as stable as we once thought. Gravitational interactions between planets, stars, and other objects can easily destabilize a system, causing planets to be ejected into space. This instability might be more common in younger planetary systems, where planets are still migrating and settling into their final orbits. Over time, these systems might eject more planets, leading to a galaxy teeming with rogue planets. Additionally, the existence of rogue planets highlights the incredible diversity of planetary environments that could exist in the universe. While planets and star systems experience relatively predictable cycles of day and night, seasons, and stellar radiation, rogue planets exist in a state of constant darkness and cold. Yet, despite these harsh conditions, they might still be capable of supporting life, particularly if they have thick atmospheres or subsurface oceans. The discovery of life on a rogue planet would represent a profound shift in our understanding of what is necessary for life to exist, expanding the range of environments where we might search for extraterrestrial life. In fact, rogue planets might even offer a unique opportunity for the development of life. Free from the intense radiation and stellar winds that affect planets in close proximity to stars, rogue planets might provide a stable, long-term environment for life to evolve. On Earth, life has been incredibly resilient, adapting to a wide range of extreme conditions. If rogue planets possess internal heat sources or subsurface oceans, they could provide a similar refuge for life, allowing it to persist even in the cold, dark expanse of space. The potential for life on rogue planets raises fascinating questions about how life could originate and thrive in such isolated and extreme environments. Traditional models of life's origins often emphasize the importance of stellar radiation, particularly sunlight, in powering the biochemical reactions that make life possible. On Earth, sunlight drives photosynthesis, which forms the basis of most food chains. In the absence of a parent star, rogue planets would lack this source of energy, prompting scientists to explore alternative pathways for life to emerge and sustain itself. One possibility is that life on rogue planets could rely on chemosynthesis, a process used by certain microorganisms on Earth. Instead of using sunlight to produce energy, these organisms derive their energy from chemical reactions involving compounds such as hydrogen sulfide or methane. On Earth, chemosynthetic organisms are found in extreme environments, such as deep-sea hydrothermal vents, where sunlight cannot reach. These vents spew out mineral-rich, superheated water, providing the necessary energy for chemosynthetic life forms to thrive. If rogue planets possess similar geological activity, with volcanic vents or fissures releasing chemical compounds, chemosynthesis could be a viable means for life to survive. Moreover, some rogue planets might have surface features that further support the possibility of life. For instance, volcanic activity could play a significant role in creating habitable environments by releasing gases into the atmosphere, contributing to both heat retention and the availability of chemical energy. Volcanic landscapes could also feature liquid water in the form of geothermal hot springs or subsurface reservoirs, which might remain in a liquid state due to the internal heat of the planet. These pockets of liquid water, combined with chemical-rich environments, could offer niches where microbial life could thrive, protected from the extreme conditions on the surface. It's even possible that some rogue planets could support extremophiles, organisms that thrive in extreme conditions. On Earth, extremophiles have been found in some of the harshest environments, from the acidic waters of volcanic lakes to the frozen tundras of Antarctica. These resilient life forms can survive in conditions that would be inhospitable to most other forms of life. On rogue planets, extremophiles could adapt to the cold, dark, and chemically rich environments, making use of the limited resources available. The discovery of such life would have profound implications for astrobiology, suggesting that life can exist in far more diverse and challenging environments than previously thought. One intriguing concept is that rogue planets could serve as potential refuges for life in the galaxy. If life exists on a rogue planet, it could be isolated from the destructive forces that often threaten life on planets within star systems, such as solar flares, gamma-ray bursts, or supernova explosions. While these events can devastate planets close to their parent stars, rogue planets, drifting through interstellar space, would be largely unaffected. This isolation could provide a stable, long-term environment for life to persist, even as nearby star systems experience cataclysmic events. In this sense, rogue planets could act as oases of life in the vast, harsh desert of space. The sheer number of rogue planets that may exist in the galaxy further increases the chances of finding life on one of these wandering worlds. Estimates suggest that there may be more rogue planets in the Milky Way than there are stars, meaning that these objects are not rare but rather a common occurrence in our galaxy. If even a small fraction of these planets have the right conditions for life, the total number of potentially habitable rogue planets could be staggering. This abundance of rogue planets suggests that the search for life beyond Earth should not be limited to planets orbiting stars, but should also include these free-floating worlds. However, the search for life on rogue planets presents unique challenges due to their dark, distant nature. Without the light of a parent star, rogue planets are incredibly difficult to detect, and any signs of life would be even more elusive. One approach might involve searching for biosignatures in the atmosphere of rogue planets, chemical compounds that indicate the presence of life. For example, the detection of gases such as oxygen, methane, or even complex organic molecules could suggest biological activity on a rogue planet. However, detecting these signatures from such a distant, faint object would require advanced technology, possibly beyond what we currently have. One promising tool in the search for rogue planets is the upcoming James Webb Space Telescope, JWST, which is designed to study the universe in infrared wavelengths. The JWST's sensitivity to infrared radiation could allow it to detect the faint heat signatures of rogue planets, even those far from any star. This would enable astronomers to study the atmospheres of these planets in greater detail, searching for signs of water vapor, methane, and other gases that could indicate the presence of life. By using instruments like the JWST, we may finally be able to detect rogue planets more efficiently and learn more about their potential habitability. In addition to finding life, the study of rogue planets could offer critical insights into the dynamics of planetary systems. Rogue planets provide a unique window into the processes of planetary ejection, migration, and system instability. By studying how rogue planets form and how they are ejected from their original systems, scientists can gain a deeper understanding of the forces that shape planetary systems as a whole. This knowledge could also help us better understand the future evolution of our own solar system, as well as the potential fate of Earth. Some theories suggest that as planetary systems age, they may become increasingly unstable, leading to the ejection of planets. For example, if the gravitational interactions between Jupiter, Saturn, and other outer planets in our solar system were to change over time, it's conceivable that one or more of these planets could be flung out into space, becoming rogue planets. This long-term instability might be a common feature of many star systems, implying that rogue planets could represent the final stages of planetary evolution. Interestingly, there is even a possibility that our solar system could capture a rogue planet at some point in the distant future. If a rogue planet were to pass close enough to the solar system, it could be captured by the sun's gravity and become a part of our planetary family. This would radically alter the dynamics of the solar system, potentially leading to gravitational disturbances that could affect the orbits of existing planets. Such an event would also offer a rare opportunity for direct study of a rogue planet in our cosmic backyard. The existence of rogue planets also raises philosophical and existential questions about the nature of planetary systems, life, and the universe itself. These lonely, drifting worlds remind us of the vastness and isolation of space, challenging our assumptions about what constitutes a planet and where life might be found. They push us to expand our search for life beyond the traditional boundaries of star systems, encouraging us to consider the possibility that life could exist in the most unexpected places. Moreover, rogue planets challenge our understanding of the cosmic order. For much of human history, the concept of a planet was closely tied to the idea of a celestial body orbiting a star. The discovery of rogue planets forces us to reconsider this definition, as these objects exist independently of any star, wandering the galaxy in isolation. This realization has profound implications for how we categorize and understand the objects in the universe, suggesting that the lines between stars, planets, and other celestial bodies may be more fluid than previously thought. As we continue to explore the universe and discover new types of celestial objects, rogue planets will likely play an increasingly important role in our understanding of planetary science and astrobiology. These mysterious, wandering worlds hold the key to unlocking new insights about the formation of planets, the potential for life in extreme environments, and the dynamic processes that shape the galaxy. Whether they serve as cosmic time capsules, refuges for life, or examples of planetary instability, rogue planets offer a wealth of opportunities for scientific discovery. In the coming years, with advances in technology and observational techniques, we will likely learn much more about these enigmatic planets. The study of rogue planets may eventually reveal secrets about the early history of planetary systems, the potential for life in the galaxy, and the ultimate fate of planets in a dynamic and ever-changing universe. For now, rogue planets remain some of the most mysterious and compelling objects in the cosmos, inviting us to look beyond the familiar and explore the unknown reaches of space. As we delve deeper into the mysteries surrounding rogue planets, one of the most intriguing aspects is their potential to offer a glimpse into the untold history of planetary formation and evolution. Unlike planets bound to stars, rogue planets carry with them a sense of cosmic anonymity, making them harder to categorize, but also more alluring in terms of what they might reveal. Their very existence challenges the conventional wisdom regarding how planets form and remain within their stellar systems. To understand the significance of rogue planets in this context, we must first revisit the core theories of planetary formation. The predominant model, known as the core accretion theory, suggests that planets form within the protoplanetary disk, a disk of gas and dust that surrounds a young star. Over time, particles within this disk collide and clump together, gradually forming larger bodies that eventually become planets. This model generally assumes that these planets will remain gravitationally bound to their parent star. However, rogue planets represent a deviation from this standard model, and their existence prompts scientists to consider alternative pathways for planetary formation and evolution. One possibility is that rogue planets are formed through a process known as gravitational instability. In this scenario, rather than forming slowly over time from the accumulation of particles, rogue planets could form almost instantaneously from the collapse of a dense region within a protoplanetary disk or even a molecular cloud. If the collapsing region is sufficiently massive, it could bypass the traditional planet formation process and form a rogue planet directly, without ever becoming bound to a star. This would mean that rogue planets could be fundamentally different from the planets we know, having formed under entirely different conditions. Another theory suggests that rogue planets may have formed in a star system, like most planets, but were later ejected due to gravitational interactions. This could happen in a variety of ways. For instance, in multi-planet systems, close encounters between planets can result in one planet being ejected from the system entirely, while the others settle into more stable orbits. This process of planetary ejection could be relatively common in the chaotic early stages of planetary system formation, when multiple planets are jockeying for position within a crowded, dynamically unstable system. As a result, rogue planets might be a natural byproduct of planetary system evolution. There is also the possibility that rogue planets could be captured worlds, planets that formed around a star but were later captured by the gravitational influence of another star or system, only to be ejected once again. In this scenario, a rogue planet might pass close enough to a star system to become temporarily gravitationally bound to it, perhaps even interacting with the planets within that system, before being flung out into interstellar space. This process could result in rogue planets that have complex and varied histories, having interacted with multiple stars and planetary systems over time. The ejection of rogue planets from their original systems raises another important question: how common is planetary ejection, and what role does it play in the evolution of planetary systems? Some simulations suggest that planetary ejection could be a relatively frequent event, particularly in systems with multiple giant planets. In these systems, gravitational interactions between the planets can lead to significant instabilities, causing some planets to be ejected while others settle into more stable orbits. If this process is common, it could mean that many planets, perhaps even a majority, are ejected from their systems over the course of billions of years, eventually becoming rogue planets. Interestingly, rogue planets could offer clues about the early history of planetary systems, including our own solar system. Some models suggest that during the early stages of the solar system's formation, there may have been more planets than we currently observe. Over time, gravitational interactions between the giant planets, Jupiter, Saturn, Uranus, and Neptune, may have led to the ejection of one or more planets from the solar system. These lost planets could still be out there, drifting through interstellar space as rogue planets. Studying rogue planets could, therefore, provide indirect evidence of these lost members of the solar system. In fact, some scientists have speculated that the hypothetical Planet 9 in our solar system, a proposed planet thought to be responsible for the unusual orbits of certain trans-Neptunian objects, could actually be a captured rogue planet. If true, this would mean that a rogue planet could have been incorporated into our solar system at some point in the past, influencing the orbits of other distant objects in the Kuiper Belt and beyond. While this theory remains speculative, it highlights the potential for rogue planets to play a significant role in shaping the dynamics of planetary systems, even long after they have been ejected from their original systems. The potential discovery of a rogue planet within our own solar system would be a monumental event, offering a rare opportunity to study such an object up close. It would allow scientists to analyze its composition, atmosphere, and surface features in unprecedented detail, shedding light on the processes that govern rogue planets and their interactions with other celestial bodies. This discovery could also provide valuable insights into the broader population of rogue planets in the galaxy, helping to refine estimates of their abundance and distribution. In addition to their scientific significance, rogue planets also capture the imagination due to their sheer isolation. These wandering worlds are often described as nomadic or orphan planets, evoking a sense of cosmic loneliness. Without the stabilizing influence of a parent star, rogue planets drift through the galaxy, exposed to the harsh environment of interstellar space. This isolation raises profound philosophical questions about the nature of existence and the role of planets in the universe. In many ways, rogue planets are the ultimate outsiders in the cosmic order. They challenge our understanding of what it means to be a planet, and they push the boundaries of where we expect to find planets and life. Their very existence forces us to reconsider the traditional categories that have long defined our understanding of the universe, suggesting that the cosmos is far more diverse and unpredictable than we might have imagined. One of the most exciting aspects of rogue planets is the possibility that they could harbor life, even in the absence of a parent star. While it may seem counterintuitive to think that life could exist on a planet without sunlight, the discovery of extremophiles on Earth has shown that life can thrive in some of the most inhospitable environments imaginable. From the deep-sea hydrothermal vents to the acidic waters of volcanic lakes, extremophiles have adapted to survive in conditions that would be deadly to most other forms of life. Rogue planets could offer similarly extreme environments, where life might find a way to persist despite the absence of sunlight. In particular, the possibility of subsurface oceans on rogue planets opens up intriguing possibilities for the existence of life. These oceans, insulated by thick layers of ice and rock, could remain liquid due to the planet's internal heat, providing a stable environment where life could develop and evolve. If life exists in these hidden oceans, it would likely be microbial in nature, similar to the chemosynthetic life forms found near hydrothermal vents on Earth. Another possibility is that rogue planets could host life forms that rely on entirely different energy sources than those we are familiar with. For example, some scientists have speculated that life on rogue planets could be powered by radioactive decay, which generates heat from the breakdown of unstable isotopes. This heat could be sufficient to maintain liquid water and drive chemical reactions, providing a potential energy source for life in the absence of sunlight. Alternatively, life on rogue planets could rely on geothermal energy from volcanic activity, using the heat and chemicals released by volcanic vents to sustain themselves. The discovery of life on a rogue planet would have profound implications for our understanding of the universe and the potential for life beyond Earth. It would suggest that life can exist in far more diverse and extreme environments than we currently imagine, expanding the range of planets and moons that might be considered habitable. Moreover, it would raise the possibility that rogue planets could serve as refuges for life in the galaxy, providing isolated, stable environments where life can persist even in the face of cosmic catastrophes. In this sense, rogue planets could play a crucial role in the long-term survival of life in the universe. While planets within star systems are subject to a variety of threats, including supernova explosions, gamma-ray bursts, and stellar flares, rogue planets are largely insulated from these dangers. Their isolation in interstellar space makes them less vulnerable to the violent events that can destroy life on planets orbiting stars. This isolation could allow life on rogue planets to persist for billions of years, even as nearby star systems undergo dramatic changes. The search for life on rogue planets is still in its early stages, but advances in technology and observational techniques could bring us closer to discovering these hidden worlds. The James Webb Space Telescope, for example, will be able to detect the faint heat signatures of rogue planets, even those far from any star. This capability could allow scientists to study the atmospheres and surfaces of rogue planets in greater detail, searching for signs of water, methane, and other compounds that might indicate the presence of life. The study of rogue planets and their potential to harbor life introduces a unique avenue in the search for extraterrestrial life. If we imagine the sheer number of rogue planets potentially drifting through the galaxy, the odds of finding life on one of these wandering worlds increase significantly. Traditional searches for life have focused on planets within the so-called habitable zone around stars, where liquid water can exist due to the right balance of warmth from the star. But rogue planets, far removed from any star, force us to rethink what we define as habitable environments. As mentioned before, the potential for subsurface oceans on rogue planets makes them particularly interesting candidates for harboring life. Consider the icy moons of our own solar system, Europa and Enceladus, both of which are believed to have vast subsurface oceans beneath thick layers of ice. Even though these moons orbit far from the Sun, their internal heat, possibly generated by tidal forces from their parent planets, could keep these oceans liquid. In a similar manner, rogue planets could possess internal heat from radioactive decay or geothermal activity that might keep water beneath their surface in a liquid state, providing the conditions necessary for life to arise and thrive. Even in the absence of such internal heating, rogue planets might still maintain an atmosphere thick enough to insulate and trap heat. For example, a dense atmosphere rich in greenhouse gases like carbon dioxide could retain heat generated from the planet's formation or residual heat from its ejection from a star system. If this heat is sufficient, it could prevent the planet's surface from freezing solid, enabling liquid water or even other exotic liquids to exist for extended periods. Such a planet could potentially sustain life even in the deep freeze of interstellar space. This scenario expands our notion of where life might exist in the universe. Scientists have long speculated that the so-called biosignature gases in a planet's atmosphere could be indicative of biological processes. If a rogue planet possesses a thick atmosphere, studying its chemical composition might provide hints of biological activity. For instance, the detection of methane or oxygen in the atmosphere of a rogue planet would be an exciting clue, as these gases are often produced by living organisms on Earth. Instruments like the James Webb Space Telescope or future space missions could be capable of detecting these biosignature gases, even in the thin atmospheres of distant rogue planets. Furthermore, the potential discovery of rogue planets that host primitive or microbial life forms could redefine our understanding of life's adaptability. It would support the theory that life can emerge and persist in environments far more extreme than previously thought. The implications of such a discovery would be staggering. Not only would it mean that life exists elsewhere in the universe, but it would also imply that life might be far more common than we currently believe. Rogue planets could be scattered throughout the galaxy, each potentially harboring life in some form, suggesting that the universe is teeming with biological diversity. The possibility of life on rogue planets also touches on a fundamental question in astrobiology. Is life a common outcome of planetary evolution, or is it an extraordinarily rare event? If rogue planets are found to host life, it would suggest that life is a robust and adaptable phenomenon, capable of arising in a variety of conditions beyond the traditional habitable zones. On the other hand, if rogue planets are found to be lifeless, it might support the view that life is an exceedingly rare occurrence, dependent on a narrow set of conditions that are difficult to find in the vastness of the universe. Beyond the search for life, rogue planets offer a unique opportunity to study planetary atmospheres and geological processes in isolation. Unlike planets that orbit stars, rogue planets do not experience the same degree of external forces, such as radiation and stellar winds, that can influence a planet's atmosphere and surface over time. This isolation allows scientists to observe planetary processes in their most unaltered state, free from the confounding effects of a nearby star. As a result, rogue planets could serve as natural laboratories for studying the atmospheric chemistry and geology of planets in a more pristine environment. For instance, studying the atmospheres of rogue planets could provide insights into how planetary atmospheres evolve in the absence of stellar influences. On Earth and other planets, the presence of a nearby star affects atmospheric composition, temperature, and weather patterns. Without the heat and radiation from a star, rogue planets would have very different atmospheric dynamics. Understanding these dynamics could help scientists refine their models of planetary atmospheres, leading to a deeper understanding of how atmospheres evolve over time, both in star systems and in isolation. Similarly, the geological features of rogue planets could reveal important clues about their formation and history. On Earth, geological activity such as volcanism and plate tectonics is driven in part by the heat generated by the sun. Rogue planets, however, would rely solely on internal sources of heat, such as radioactive decay or residual heat from their formation. Studying the surface features of rogue planets could help scientists understand how geological processes operate in the absence of a star, providing valuable insights into the interior structure and evolution of these mysterious worlds. There is also the tantalizing possibility that some rogue planets could have magnetic fields, similar to Earth's magnetic field, which protects our planet from harmful solar radiation. A planet with a strong magnetic field could maintain a stable atmosphere over long periods, even in the cold vacuum of interstellar space. This magnetic field could also provide additional protection for any life forms that might exist on the planet, shielding them from cosmic rays and other forms of radiation. The detection of a magnetic field on a rogue planet would be a major breakthrough, as it would suggest that such planets have active cores and are capable of maintaining habitable conditions for extended periods. The potential for rogue planets to possess magnetic fields also raises questions about the role of planetary magnetism in the evolution of life. On Earth, the magnetic field is believed to play a crucial role in protecting life from the harmful effects of solar radiation. If rogue planets can generate and sustain magnetic fields, it could suggest that planetary magnetism is a more common feature of planets than previously thought, and that it plays a key role in the long-term habitability of planets, even those far removed from any star. Another exciting possibility is that rogue planets could harbor exotic forms of matter or even entirely new types of geological formations that do not exist on planets bound to stars. In the extreme conditions of interstellar space, where temperatures can drop to near absolute zero, the materials that make up a rogue planet's surface could behave in ways that are entirely different from what we observe on Earth. For example, ice on a rogue planet might take on unusual crystalline structures due to the extreme cold, while metals and other materials could exhibit properties not seen under normal planetary conditions. Studying these materials could lead to new discoveries in the field of planetary science and provide insights into the fundamental nature of matter under extreme conditions. The potential for discovering new types of geological formations on rogue planets also opens the door to the study of planetary evolution in entirely new contexts. For example, rogue planets that formed in the dense regions of star-forming molecular clouds might have experienced very different environmental conditions during their early history compared to planets that formed around stars. These differences could manifest in the form of unique surface features or mineral compositions that are not found on other planets. By studying these features, scientists could gain a better understanding of the processes that shape planetary formation and evolution across a wide range of environments. The possibility of finding new types of matter or geological formations on rogue planets also raises intriguing questions about the potential for technological advancements. If rogue planets possess materials with unusual properties, these materials could have applications in fields such as superconductivity, quantum computing, or even space exploration. For example, the discovery of a new type of superconductor on a rogue planet could revolutionize the way we build electronic devices, while the identification of new structural materials could lead to stronger, lighter spacecraft capable of exploring the farthest reaches of the galaxy. The exploration of rogue planets is still in its infancy, but the potential for groundbreaking discoveries is immense. With advancements in technology, such as next-generation telescopes and space probes, we are on the cusp of a new era in the study of these enigmatic worlds. As we continue to search the cosmos for rogue planets, we may find that these wandering worlds hold the key to some of the greatest mysteries of planetary science, including the origins of planets, the potential for life beyond Earth, and the nature of matter under extreme conditions. The discovery of rogue planets has already challenged many of the assumptions we once held about the formation and evolution of planets. As we continue to explore these uncharted worlds, we are likely to uncover even more surprises that will reshape our understanding of the universe and our place within it. Whether rogue planets turn out to be barren, lifeless rocks, or fertile grounds for life, their study will undoubtedly yield valuable insights into the workings of the cosmos. offering a deeper appreciation for the complexity and diversity of the universe. The exploration of rogue planets might also open new avenues for space travel and exploration. Rogue planets drifting through interstellar space could serve as waypoints for future missions beyond our solar system. Imagine a scenario where humanity embarks on deep space exploration missions to nearby star systems, only to discover rogue planets along the way. These planets, even though they are not orbiting a star, could provide resources such as water, rare minerals, or even energy sources that would be invaluable for long-duration space missions. Rogue planets might act as stepping stones in the vast expanse of space, enabling future spacecraft to refuel or even establish temporary bases. This possibility introduces a fascinating concept for the future of space exploration. Traditional space missions rely heavily on planning around known celestial objects like planets, moons, and asteroids that orbit stars. However, if we can map out the locations of rogue planets, we could fundamentally change how interstellar travel is planned. Rogue planets could provide rest stops, enabling ships to traverse the immense distances between star systems more efficiently. Rather than carrying all necessary supplies from Earth, future spacefarers could harvest resources from rogue planets, cutting down on the size and cost of space missions. Additionally, rogue planets could act as natural laboratories for testing new technologies for planetary exploration and colonization. Since rogue planets are isolated from the harmful radiation of stars, they could serve as safer environments for testing human habitats and life support systems for long-term survival in deep space. These planets would provide real-world conditions for experimenting with sustainable living techniques that could eventually be used on more distant planetary bodies like Mars or exoplanets. If a rogue planet with significant resources were found, it could become a focal point for human expansion beyond the solar system. Colonizing a rogue planet might seem like a strange concept at first, given their cold and dark environments, but with advancements in energy generation and life support technology, such a planet could become habitable. Artificial light sources, geothermal energy, or fusion reactors could provide the energy needed to maintain life on a rogue planet. This would be an unprecedented achievement in human history, as it would mark the first instance of colonizing a world entirely independent of a star. In addition to its role in space exploration, the study of rogue planets can teach us more about the fate of planetary systems over time. Our solar system, like other star systems, will not remain as it is forever. Over billions of years, gravitational interactions between planets, moons, and the sun will change, and it is possible that some planets may eventually be ejected from the solar system and become rogue planets themselves. By studying rogue planets, we gain insight into what might happen to our own planet or others in the far future. This leads to another important question: could Earth, one day, become a rogue planet? While this scenario is not likely to occur for billions of years, it is not entirely impossible. Over extremely long time frames, gravitational forces from passing stars or other cosmic events could destabilize planetary orbits, potentially ejecting planets like Earth from the solar system. If Earth were to become a rogue planet, its fate would depend on several factors, including its internal heat, atmosphere, and the ability of life to adapt to the absence of sunlight. Even if Earth were to be ejected from the solar system, it would retain its internal heat for some time, particularly if its core remains active. This heat, along with a thick atmosphere, might be enough to sustain life in some form, much like the scenarios we imagined for other rogue planets. While the surface of the planet would likely freeze, subsurface environments could remain warm and habitable, similar to the conditions we speculate might exist on rogue planets with subsurface oceans. The idea of Earth becoming a rogue planet might seem far-fetched, but it underscores the importance of studying these wandering worlds. By understanding the mechanisms that lead to the formation of rogue planets, we can better predict the long-term evolution of planetary systems, including our own. Rogue planets serve as a reminder that the universe is dynamic, constantly shifting, and that planets are not permanently bound to the stars they orbit. As we continue to study rogue planets, we may also uncover clues about the history of our galaxy. Rogue planets could carry with them the signatures of the environments in which they formed, providing a fossil record of sorts for the conditions present in the early galaxy. By studying the chemical composition of rogue planets, scientists can learn more about the processes that shaped the galaxy billions of years ago, before planets were ejected from their star systems. For instance, if a rogue planet formed in a region of the galaxy rich in heavy elements, its composition could reflect that environment, offering clues about the types of stars that existed in that region during its formation. Conversely, if a rogue planet is found to be composed primarily of lighter elements, it could indicate that the planet formed in a more ancient part of the galaxy where fewer heavy elements were present. In this way, rogue planets can act as time capsules, preserving a snapshot of the galaxy's past and helping scientists piece together the history of planetary formation. The study of rogue planets could also shed light on the mysterious process of planet formation itself. Traditional models of planet formation suggest that planets formed from the protoplanetary disks of gas and dust that surround young stars. However, the existence of rogue planets challenges this view, as it suggests that planets can form in isolation without the presence of a star. This raises important questions about the mechanisms by which planets coalesce from raw materials and whether planet formation is a more flexible and varied process than previously thought. One possibility is that rogue planets formed in star systems but were later ejected through gravitational interactions. Alternatively, rogue planets may have formed directly in interstellar space, coalescing from clouds of gas and dust that never condensed into stars. If this is the case, it would suggest that planet formation is not solely dependent on the presence of a star, but can occur in a variety of environments. This would expand our understanding of how planets form and highlight the diversity of planetary systems in the galaxy. The discovery of rogue planets also has implications for the search for extraterrestrial intelligence, SETI. If rogue planets are common throughout the galaxy, they could provide a new avenue for the search for alien civilizations. Traditionally, SETI has focused on searching for signals from planets orbiting stars, but rogue planets, with their isolation and unique conditions, could host advanced civilizations that have adapted to life without the presence of a star. These civilizations might have developed technologies that allow them to harness geothermal energy or other sources of power, enabling them to thrive on rogue planets. Searching for signals from rogue planets would be a challenging task, as these planets are much more difficult to detect than those orbiting stars. However, advancements in technology, such as more sensitive radio telescopes and space-based observatories, could make it possible to detect signs of intelligent life on rogue planets. The discovery of such a civilization would be one of the most profound events in human history, challenging our assumptions about the conditions necessary for life and intelligence to arise. In addition to the search for extraterrestrial intelligence, the study of rogue planets could help us understand the potential risks and challenges of future human space exploration. Rogue planets, with their extreme environments and lack of sunlight, present a unique set of challenges for survival. By studying these planets, we can develop new technologies and strategies for coping with the harsh conditions of space, preparing us for future missions to distant star systems or even other rogue planets. For example, the development of advanced life support systems capable of functioning in the cold and dark environments of rogue planets could be invaluable for long-duration space missions. Similarly, the study of geothermal energy on rogue planets could lead to new ways of generating power in space, enabling spacecraft and habitats to remain self-sufficient in the absence of sunlight. These advancements would not only benefit future space missions, but could also have applications here on Earth, particularly in remote or extreme environments where traditional power sources are not available. Ultimately, the study of rogue planets represents one of the most exciting frontiers in modern astronomy. These mysterious worlds challenge our understanding of planetary science, offer new possibilities for the search for life, and provide valuable insights into the history and future of our galaxy. As we continue to explore the cosmos, rogue planets will undoubtedly play a key role in shaping our understanding of the universe and our place within it. As we delve deeper into the study of rogue planets, it's essential to consider the potential for future discoveries and how they may impact our understanding of the universe. Ongoing advancements in astronomical technology will likely play a significant role in our ability to detect and study these elusive worlds. The implementation of next-generation telescopes and space observatories, such as the James Webb Space Telescope, JWST, will revolutionize our exploration of rogue planets. The JWST is designed to observe the universe in infrared wavelengths, allowing scientists to peer through dust clouds and gather data on distant celestial objects, including rogue planets. With its ability to analyze the atmospheres of exoplanets, JWST could potentially identify chemical signatures indicative of life on these wandering worlds. While the telescope's primary focus is on star systems and their planets, its capabilities will undoubtedly extend to rogue planets, enabling researchers to uncover the mysteries surrounding their formation and characteristics. Another promising avenue for rogue planet research is the development of more sensitive detection methods. Current techniques primarily rely on the gravitational effects that rogue planets exert on nearby celestial objects, such as stars or other planets. By observing these gravitational interactions, scientists can infer the presence of a rogue planet and estimate its mass and orbit. Future advancements in gravitational wave detection and precision astrometry may provide even more powerful tools for locating and characterizing rogue planets. In addition to improving detection methods, future research efforts will focus on the classification and categorization of rogue planets. Just as we have a diverse array of planets within our solar system and among known exoplanets, rogue planets may also exhibit a wide variety of characteristics and compositions. Classifying these planets could reveal important trends in their formation and evolution, helping scientists better understand the mechanisms that govern planetary dynamics. As we gather more data on rogue planets, scientists may also explore their potential connections to other astronomical phenomena. For example, the study of rogue planets could be linked to our understanding of black holes and their role in shaping planetary systems. Some theories suggest that black holes could eject planets from their original star systems, leading to the formation of rogue planets. Investigating this relationship could provide valuable insights into the life cycle of stars and planets and how they interact within the larger cosmic framework. Furthermore, the study of rogue planets may enhance our knowledge of dark matter and dark energy, two of the most profound mysteries in astrophysics. Dark matter is believed to comprise a significant portion of the universe's mass, yet it remains invisible and undetectable through conventional means. Understanding how rogue planets fit into the context of dark matter might reveal new ways to probe this enigmatic aspect of the universe. For instance, if rogue planets are influenced by dark matter, studying their movements and distributions could offer clues about the nature of this elusive substance. In exploring the potential for future colonization of rogue planets, researchers are considering various methods for making these worlds habitable. One approach is terraforming, which involves modifying the environment of a celestial body to make it more Earth-like. While terraforming is often associated with Mars, it could also apply to rogue planets. For example, scientists could explore ways to introduce greenhouse gases to warm the surface of a rogue planet, potentially creating a more hospitable environment. Additionally, the idea of creating self-sustaining habitats on rogue planets is gaining traction. As technology advances, we may develop innovative life support systems capable of generating food, water, and oxygen independently of stellar energy. This technology could enable future human settlements to thrive on rogue planets, even in the absence of sunlight. By utilizing geothermal energy and closed-loop ecological systems, we could potentially establish thriving colonies in the dark depths of space. The implications of rogue planets extend beyond the realm of planetary science. They also challenge our philosophical and existential perspectives. The existence of these lonely worlds raises profound questions about the nature of life and consciousness. If intelligent life can arise on a rogue planet, isolated from the warmth and light of a star, what does that say about the conditions necessary for life to flourish? This challenges our preconceived notions and highlights the resilience of life in the face of adversity. Moreover, the discovery of rogue planets with signs of life could redefine our understanding of the universe's diversity. The idea that life can thrive in extreme conditions invites us to reevaluate our search criteria for extraterrestrial intelligence. If life can exist in the darkness of interstellar space, it broadens the scope of potential habitats we must consider in our search for alien civilizations. As the search for rogue planets continues, scientists and astronomers are developing collaborative efforts to share data and research findings. International partnerships, such as those between space agencies and universities, are vital for advancing our understanding of these mysterious worlds. By pooling resources and expertise, researchers can accelerate the pace of discovery and enhance our collective knowledge of rogue planets. The exploration of rogue planets serves as a testament to humanity's curiosity and ingenuity. As we continue to push the boundaries of our understanding, the study of these wandering worlds promises to reshape our view of the universe and our place within it. Each new discovery brings us closer to answering some of the most fundamental questions about existence, the formation of planetary systems, and the possibility of life beyond our solar system. Rogue planets represent one of the most intriguing mysteries in modern astronomy. These solitary worlds, unbound by the gravitational pull of a star, challenge our understanding of planetary formation, evolution, and the potential for life. As we advance our technological capabilities and deepen our understanding of the cosmos, the study of rogue planets will undoubtedly lead to exciting discoveries and profound revelations. Whether as potential habitats for future colonization, clues to the history of our galaxy, or insights into the nature of life itself, rogue planets will continue to capture our imagination and inspire our quest for knowledge. The universe remains full of surprises, and the exploration of rogue planets is just one chapter in the ever-unfolding story of cosmic discovery. In addition to the exploration of rogue planets, it's important to recognize the cultural and scientific significance they hold for humanity. The study of these isolated worlds not only pushes the boundaries of our scientific knowledge, but also fuels the imagination and curiosity that have driven human exploration for centuries. As we ponder the existence of rogue planets, we are reminded of our place in the universe and our ongoing quest to understand the unknown. The notion of a rogue planet also sparks various cultural and philosophical discussions. In literature and art, rogue planets have often been depicted as symbols of isolation and the unknown. They challenge our perception of home, safety, and the importance of a stable environment for life. This resonates with existential themes that have been explored by writers and philosophers throughout history. The idea that life might exist in the cold, dark expanse of space raises profound questions about our understanding of what it means to be alive and how we define our existence. From a scientific perspective, rogue planets are valuable for testing our theories of planet formation and migration. Understanding how these planets come to exist can illuminate the processes that govern not just rogue planets but also the behavior of planets within stable star systems. This has implications for our models of planetary dynamics, formation, and the stability of planetary orbits. As we gather more data on rogue planets, we may uncover patterns that could inform our understanding of how other celestial bodies, including those within our own solar system, have evolved. As we contemplate the future of rogue planet research, we must also consider the ethical implications of exploring and potentially colonizing these distant worlds. If we were to discover life on a rogue planet, what responsibilities would we have toward it? How would our actions impact these ecosystems? These questions emphasize the importance of adopting an ethical framework for our scientific pursuits, ensuring that we respect the potential life forms we may encounter. Moreover, the search for rogue planets contributes to our broader understanding of the universe's structure and composition. By studying the distribution and characteristics of these planets, scientists can gain insights into the formation and evolution of galaxies. The dynamics of rogue planets may reveal the processes that govern galaxy formation and the interactions between stars and their planets. This knowledge can inform our understanding of the cosmos as a whole and the forces that shape it. Additionally, rogue planets could play a role in the search for extraterrestrial intelligence, SETI. As we expand our criteria for finding life, rogue planets might become candidates for exploration. The discovery of life on a rogue planet would fundamentally alter our understanding of where and how life can exist in the universe. It would also open new avenues for exploring the potential for intelligent civilizations in unexpected environments. The development of sophisticated models and simulations will play a crucial role in rogue planet research. Researchers can create detailed simulations that mimic the formation and behavior of rogue planets within various cosmic environments. By analyzing the results of these simulations, scientists can refine their theories and make predictions about the properties of rogue planets that may exist beyond our observational reach. In the quest to understand rogue planets, interdisciplinary collaboration will be key. Astronomers, physicists, geologists, and biologists must work together to create a comprehensive understanding of these mysterious worlds. By combining expertise from various fields, researchers can tackle the complex questions surrounding rogue planets and explore their potential implications for life beyond Earth. Public engagement and education will also be vital in fostering interest in rogue planet research. As the mysteries of these celestial bodies capture the imagination of the public, educational initiatives can inspire the next generation of scientists and explorers. Outreach programs, public lectures, and interactive exhibits can raise awareness of the importance of rogue planet research and its implications for our understanding of the universe. The fascination with rogue planets extends to the realm of popular culture. Films, television shows, and video games have all drawn inspiration from the concept of isolated planets drifting through the cosmos. These portrayals often reflect our fears and aspirations, prompting us to ponder the unknown and our place within the vast universe. By weaving scientific concepts into storytelling, we can bridge the gap between complex scientific ideas and the public's understanding of them. As we continue to explore the cosmos and unravel its mysteries, rogue planets will undoubtedly remain a topic of interest for scientists and enthusiasts alike. The quest to understand these wandering worlds is not just a scientific endeavor, it is a reflection of our innate curiosity and desire to explore the unknown. Each new discovery brings us closer to unraveling the secrets of the universe and understanding our role within it. In summary, rogue planets are enigmatic celestial bodies that challenge our understanding of planetary formation, evolution, and the potential for life beyond our solar system. Their existence opens up new avenues of research, prompting us to reconsider our models of planetary dynamics and the conditions necessary for life. As we harness advanced technology, collaborate across disciplines, and engage the public in our explorations, we stand on the cusp of exciting discoveries that could reshape our understanding of the universe. The study of rogue planets is a testament to humanity's enduring quest for knowledge and understanding. As we strive to uncover the mysteries of these wandering worlds, we are reminded of the infinite possibilities that the universe holds. The journey to explore rogue planets is a journey of discovery, innovation, and wonder, a journey that will continue to inspire generations to come. As our understanding of rogue planets evolves, the implications of their existence extend into the realm of astrophysical theories. One intriguing hypothesis is that rogue planets may serve as laboratories for understanding atmospheric and geological processes in extreme environments. These isolated worlds, devoid of a star's warmth, experience unique conditions that could reveal insights into planetary formation, climate dynamics, and the potential for habitability under extreme circumstances. Studying the atmospheres of rogue planets can shed light on how planetary atmospheres evolve without the influence of a nearby star. For example, research has indicated that some rogue planets may still possess residual heat from their formation. This internal heat could create conditions for atmospheric retention, potentially allowing for complex chemical processes to occur. The investigation of these processes may provide valuable insights into the fundamental mechanisms that govern planetary atmospheres, including those of exoplanets and stable star systems. Furthermore, the geological processes of rogue planets are of particular interest. Unlike planets orbiting stars, rogue planets may lack the thermal energy required for conventional geological activity. However, internal heat generated by radioactive decay or residual heat from their formation could still drive geological processes. This raises fascinating questions about the potential for tectonic activity, volcanic eruptions, and the presence of subsurface oceans. Understanding the geological history of rogue planets could reveal critical information about planetary evolution and the conditions that lead to the formation of habitable environments. The existence of rogue planets may also prompt scientists to reevaluate our understanding of the distribution of mass in the universe. The presence of these planets could contribute to the overall mass budget of galaxies and influence the dynamics of star formation. Investigating the role of rogue planets in galaxy formation and evolution could enhance our comprehension of cosmic structures and the forces that shape them. Moreover, rogue planets might serve as analogs for other celestial phenomena. For instance, some researchers draw parallels between rogue planets and certain types of brown dwarfs, substellar objects that do not have enough mass to sustain hydrogen fusion like stars. By studying the similarities and differences between rogue planets and brown dwarfs, scientists can refine their models of substellar objects and better understand the diversity of planetary and stellar bodies in the universe. As our observational techniques continue to improve, rogue planets could reveal themselves in unexpected ways. While current methods primarily focus on gravitational effects and direct imaging, future advancements may allow for more sophisticated techniques, such as the analysis of gravitational microlensing events. This phenomenon occurs when a massive object, like a rogue planet, passes in front of a more distant star, temporarily magnifying the star's light. By studying these microlensing events, astronomers can gain valuable information about the characteristics of rogue planets and their distribution in the galaxy. The exploration of rogue planets will also necessitate the development of innovative technological solutions for future missions. For example, the design of spacecraft capable of reaching and studying these distant worlds could revolutionize our understanding of rogue planets. Advanced propulsion systems, like ion thrusters or solar sails, may enable missions that could target rogue planets, allowing scientists to gather direct data on their atmospheres, geology, and potential for life. In addition to technological advancements, international collaboration in space exploration will be critical for rogue planet research. Countries around the world are investing in space missions that focus on planetary exploration, and collaborative efforts could amplify the impact of these missions. By sharing data, expertise, and resources, nations can accelerate the pace of discovery and enhance our understanding of rogue planets. As we look toward the future of rogue planet research, the potential for interdisciplinary collaboration grows. Astrobiologists, planetary scientists, and astronomers must work together to formulate hypotheses, design experiments, and interpret data. This collaborative spirit will be essential for unraveling the complexities of rogue planets and understanding their implications for life in the universe. The scientific exploration of rogue planets is not merely an academic pursuit, it reflects humanity's desire to understand our place in the cosmos. The quest for knowledge drives us to ask fundamental questions about our existence and the conditions that foster life. The study of rogue planets encapsulates this curiosity, inviting us to consider the broader implications of life beyond Earth. As we expand our horizons, we must also engage with the ethical considerations surrounding our exploration of rogue planets and potential extraterrestrial life. The very idea of discovering life on a rogue planet raises profound questions about our responsibilities as explorers. If we were to encounter intelligent life forms or ecosystems, what obligations would we have toward them? The possibility of interacting with extraterrestrial beings necessitates a thoughtful and principled approach to exploration, ensuring that we respect their autonomy and preserve their environments. Furthermore, the existence of rogue planets invites us to reflect on the nature of exploration itself. Historically, exploration has often been driven by the desire for resources, knowledge, and power. As we venture into the cosmos, we must prioritize stewardship over exploitation. This perspective challenges us to consider how we can conduct our scientific inquiries in a way that is mindful of the integrity of the environments we explore, even those as distant as rogue planets. Rogue planets also represent a unique perspective on the concept of habitability. Traditional definitions of habitable zones revolve around the proximity to a star, where conditions are just right for liquid water to exist. However, rogue planets defy these parameters, showcasing the potential for life to thrive in the dark and cold regions of space. This realization compels us to expand our criteria for identifying potentially habitable worlds and challenges our assumptions about where life might emerge. The exploration of rogue planets can also yield insights into the processes that govern planetary system evolution. Many planetary systems experience gravitational interactions that can lead to the ejection of planets from their original orbits. By studying the characteristics of rogue planets, we can gain a deeper understanding of these dynamical processes and how they shape the architecture of planetary systems. This knowledge could inform our understanding of not only rogue planets, but also the stability and evolution of planets within star systems. Moreover, the diverse environments that rogue planets may present can enrich our understanding of planetary atmospheres. Some rogue planets might retain significant atmospheric components despite their isolation from a star. The composition and dynamics of these atmospheres can differ vastly from those of planets within stable orbits. By studying the atmospheres of rogue planets, we can explore new chemical pathways and atmospheric phenomena that could illuminate the broader principles governing planetary atmospheres across the universe. In light of these possibilities, the scientific community is increasingly recognizing the importance of rogue planets in the broader context of astrophysical research. The study of these celestial bodies may not only enhance our understanding of planetary formation and evolution, but also contribute to the development of theories related to the origins of life in the universe. As researchers delve into the complexities of rogue planets, they may uncover unexpected connections between these isolated worlds and the processes that govern the emergence of life on Earth and beyond. Public interest in rogue planets is also growing, fueled by advances in technology and the increasing visibility of scientific discoveries. Engaging the public in discussions about rogue planets can foster a sense of wonder and curiosity about the cosmos. Science communication plays a vital role in bridging the gap between scientific research and public understanding, allowing individuals to grasp the significance of rogue planet studies and their implications for humanity. Educational initiatives that highlight the mystery and intrigue surrounding rogue planets can inspire future generations of scientists and explorers. By integrating rogue planet research into curricula, educators can ignite a passion for astronomy and planetary science in students, encouraging them to explore the unknown. Such efforts can create a new wave of researchers who are equipped to tackle the challenges and questions that rogue planets present. As we continue to explore the mysteries of the cosmos, the significance of rogue planets will only grow. They serve as a reminder of the complexity and diversity of our universe, urging us to think beyond traditional definitions of habitability and planetary systems. The quest to understand these wandering worlds invites us to engage with fundamental questions about life, existence, and the forces that shape the cosmos. In conclusion, rogue planets represent a fascinating and enigmatic aspect of our universe. Their existence challenges our understanding of planetary formation, habitability, and the potential for life beyond Earth. As we embark on the journey to explore these isolated worlds, we must embrace a multidisciplinary approach that fosters collaboration, innovation, and ethical considerations. The study of rogue planets not only enhances our scientific knowledge, but also enriches our cultural and philosophical perspectives on existence. The future of rogue planet research holds immense promise, and as we venture into the unknown, we stand to uncover secrets that will redefine our understanding of the universe and our place within it. Each discovery will bring us closer to understanding the intricate tapestry of the cosmos and the diverse phenomena that populate it. The exploration of rogue planets is not merely an academic pursuit, it is a testament to humanity's enduring spirit of inquiry and exploration. As we gaze into the vastness of space and contemplate the mysteries of rogue planets, we are reminded that the universe is a complex and dynamic entity. Our pursuit of knowledge will continue to illuminate the dark corners of the cosmos, revealing wonders that have long eluded our understanding. With every advancement in technology and every new discovery, we draw closer to the profound realization that we are but one thread in the intricate web of existence, woven into the fabric of the universe. As we continue to explore the vast expanse of the universe, rogue planets serve as compelling subjects for understanding the complex dynamics of planetary systems. One important aspect of rogue planets is their potential to provide insights into the processes that lead to their ejection from their host systems. Various mechanisms may contribute to this phenomenon, including gravitational interactions with other celestial bodies, the influence of binary star systems, or the complex interactions within crowded star clusters. Gravitational interactions are among the most significant factors influencing the stability and dynamics of planetary orbits. In multi-planet systems, gravitational perturbations can cause instability in a planet's orbit, leading to potential ejection. For example, when two planets orbiting the same star experience close encounters, one planet may gain enough velocity to escape the gravitational pull of the star and become a rogue planet. Studying such interactions provides valuable insights into the evolutionary pathways of planetary systems and the potential fates of their constituent planets. Binary star systems further complicate this dynamic. In systems where two stars orbit each other closely, planets may experience significant gravitational influences that can destabilize their orbits. If a planet is located in the habitable zone of one star, its orbit could be disrupted if the other star's gravitational pull becomes significant. This scenario highlights the diverse environments in which rogue planets can originate, as well as the intricate gravitational ballet that governs their trajectories. Moreover, crowded star clusters present an additional layer of complexity. In such environments, interactions between stars and planets can lead to increased gravitational perturbations, making it more likely for planets to be ejected from their original orbits. Rogue planets resulting from these interactions could provide valuable data regarding the characteristics of the environments in which they formed, revealing how dense stellar populations influence the dynamics of planetary systems. Rogue planets also challenge traditional definitions of what constitutes a planet. In recent years, the astronomical community has debated the criteria that distinguish planets from other celestial bodies, particularly in light of discoveries like rogue planets. The International Astronomical Union, IAU, defines a planet as a celestial body that orbits a star, is spherical in shape, and has cleared its orbit of other debris. However, rogue planets defy the first criterion, prompting discussions about their classification. The existence of rogue planets has led to the emergence of alternative categorizations, suggesting that these bodies represent a distinct class of planets that exist outside the conventional definitions. This rethinking of planetary classification reflects the evolving nature of astronomical knowledge and the need for flexible frameworks that can accommodate new discoveries. Understanding rogue planets' unique characteristics may inspire a broader perspective on planetary science, emphasizing the diverse forms that planets can take in the universe. Furthermore, the study of rogue planets can enhance our understanding of the early universe. The formation of stars and planets is believed to have occurred shortly after the Big Bang, in a process influenced by cosmic evolution. As we examine rogue planets, we may uncover clues about the conditions that prevailed during the formation of planetary systems in the early universe. Investigating the chemical compositions of rogue planets, their atmospheres, and potential geological features could illuminate the processes that led to the birth of the first stars and planets, providing a glimpse into the infancy of our cosmos. Rogue planets may also be relevant to the search for extraterrestrial life, albeit in unexpected ways. While their isolation from stellar heat suggests a harsh environment, it does not eliminate the possibility of life entirely. Some scientists propose that subsurface oceans may exist on certain rogue planets, kept warm by geothermal activity. This idea aligns with the concept of extremophiles, organisms that thrive in extreme conditions, found in some of Earth's most inhospitable environments. If rogue planets can host subsurface oceans, they may harbor ecosystems unlike those found on Earth, expanding our understanding of the potential for life beyond our home planet. As we ponder the implications of rogue planets on the search for extraterrestrial life, it is essential to consider the methods we employ in this quest. Space missions designed to detect biosignatures or signs of life will need to adapt their strategies to account for the unique characteristics of rogue planets. Future telescopes and observational techniques could focus on identifying chemical signatures in the atmospheres of these planets, potentially revealing the presence of organic molecules or indicators of biological processes. The concept of habitable zones also requires reconsideration in the context of rogue planets. While traditional definitions prioritize proximity to a star, rogue planets offer a unique opportunity to explore alternative criteria for habitability. The notion of a habitable zone must be expanded to include conditions that could sustain life in the absence of sunlight, such as internal heat sources or chemical energy derived from geological processes. This broader perspective may yield new insights into the potential for life in extreme environments, guiding future research and exploration endeavors. As we delve deeper into the mysteries of rogue planets, we are also confronted with the philosophical implications of their existence. The search for life beyond Earth raises profound questions about our understanding of life itself. If we were to discover life on a rogue planet, what would it mean for our comprehension of biology and the conditions required for life to thrive? The potential for discovering radically different forms of life would challenge our assumptions and provoke discussions about the fundamental characteristics that define life in the universe. Additionally, the exploration of rogue planets evokes a sense of wonder and curiosity about the universe. These wandering worlds inspire us to imagine the possibilities that lie beyond our current understanding. The mysteries surrounding rogue planets serve as a reminder of the vastness of the cosmos and the potential for discovering new realms of existence. Our journey to uncover the secrets of these planets reflects humanity's enduring quest for knowledge and our desire to connect with the universe on a deeper level. The study of rogue planets is not just an academic pursuit, it is an exploration of our place in the cosmos. As we venture into the unknown, we gain insights into the complexities of planetary systems and the forces that shape them. Each discovery invites us to reevaluate our understanding of the universe, encouraging us to question the boundaries of what we know. In summary, rogue planets are enigmatic celestial bodies that challenge our understanding of planetary systems, formation processes, and the potential for life beyond Earth. Their existence prompts us to reconsider traditional definitions of planets and habitable environments, expanding our horizons in the search for extraterrestrial life. The study of rogue planets enriches our understanding of cosmic evolution, offering clues about the conditions that prevail in the universe. As we continue our exploration of rogue planets, we must embrace a multidisciplinary approach that incorporates advances in technology, international collaboration, and ethical considerations. The quest to unravel the mysteries of rogue planets reflects our innate curiosity and desire to comprehend the cosmos. By engaging with these enigmatic worlds, we not only enhance our scientific knowledge but also deepen our connection to the universe. The future of rogue planet research holds immense potential, and as we push the boundaries of exploration, we stand to uncover secrets that redefine our understanding of existence. Each step we take in our quest to understand rogue planets brings us closer to unlocking the mysteries of the universe and our place within it. The exploration of these wandering worlds will continue to inspire generations of scientists, thinkers, and dreamers, fueling our collective imagination as we gaze into the depths of space. In conclusion, rogue planets are a testament to the complexity and diversity of our universe. They embody the mysteries that await discovery and remind us of the vast potential for exploration and understanding. As we embark on this journey into the unknown, we are bound to encounter wonders that challenge our perceptions and expand our horizons, ultimately guiding us toward a more profound understanding of the cosmos and our place within it. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.